Hi everyone. Let's take one more example to understand the minimization process. So in this particular DFA transition diagram, there are total 8 states: Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. So Q0 to Q7, there are total 8 different states. And I have chosen this example specifically because to understand you that you do not blindly draw the transition table by looking at the transition diagram. You just observe carefully the transition diagram first and then decide whether you will take all the states in the transition table or not. Because in this particular example, if you observe carefully, this 4 states Q4 to Q7 is actually not achieved through the states Q0. What I mean to say, if you walk from Q0 and you want to go to the state Q4, Q5, Q6, Q7, you will not go to there. Why? Because here the direction of edges is from Q4 to Q3 and Q7 to Q3. But what about the direction of edges Q3 to Q4 or Q3 to Q7? There are not any direction of edges. So it means that we cannot go from Q3 to Q4 state, or we cannot go from Q3 to Q7 state. Okay? That means in the transition table of minimization process, we will consider only these 4 states: Q0, Q1, Q2 and Q3. So Q0, Q1, Q2 and Q3. And what is the initial state? Initial state is Q0 and final state is Q3. So our transition table is very much small from the whatever you see the transition diagram here. Okay, so do not blindly consider all the states and make some minimization process and give them complex. First observe the transition diagram and then draw the transition table. After that you will use the equivalent procedure and make the final minimal DFA. Okay, so on Q0, small a will go to Q1, small a will go to Q1, and on small b it will go to Q0 itself. Similarly, Q1 state on small a will go to Q0, and on small b it will go to Q2. Q2 state on Q2, if you see small a, you will go to state Q3, and on small b you will go to state Q1. Similarly, on Q3 state, if you take small a, you will go to Q3 itself, and on small b you will go to Q0. Okay, so this is the transition table. Now after making the transition table, I will use the equivalent concept. So I will erase this particular diagram because it is not required. Okay, and from this transition table I will use the equivalent concept. First I will find the zero equivalent set. So zero equivalent set is containing final state and non-final state into two different boxes. So what is final state here? Final state is Q3 and non-final state is Q0, Q1, Q2. So non-final state is Q0, Q1 and Q2, and final state is Q3. After constructing zero equivalent, I will construct one equivalent. So again the procedure is same. Compare Q0 and Q1 state, Q0 and Q1. Q0 and Q1 on a small a will go to Q1 and Q0. Q1 and Q0 will present in the same box in previous equivalent, and on a small b it will go to Q0 and Q2. It will go to Q0 and Q2. It will also present in the same box. So definitely in one equivalent Q0 and Q1 will come together and present in the same box. Now compare Q0 and Q2. Q0 and Q2 on a small a, it will go to Q1 and Q3. Here Q3 is final state. So Q3 is present in different box and Q1 is present in different box. That means Q2 is now separated and comes under a single box, and Q3 is also separated from different box. So here I have got three different boxes: Q0, Q1 as the same box, Q2 is in the different box, and Q3 in the different box. Now let's construct two equivalent. So you will go until the two subsequent equivalent set equal. If the two subsequent equivalent sets are equal, then you will stop the procedure and draw the transition diagram. So in two equivalent, I will compare A0, Q0 and Q1, Q0 and Q1. On a small a, it will go to Q1 and Q0, Q1 and Q0, which is in the same box. And on a small b, it will go to Q0 and Q2, Q0 and Q2. That means they are also separated in the two equivalent sets. So they are separated Q0. Now compare Q1 and Q2, Q1 and Q2. Q1 and Q2 is also Q0 and Q3, which is in different box. So definitely they are also not come together, and we have to make them separated Q0, Q1, Q2 and Q3. Now if you go one more step, finding three equivalent, you will find that two equivalent and three equivalent are same: Q0, Q1, Q2, Q3, because all these states are separated now. How can you find a equivalent set in which the two different separated states are come together and present in single box? This will not possible. So definitely two equivalent and three equivalent are same. So we have to stop this procedure. And now after constructing the three equivalent, there are total four different states: Q0, Q1, Q2, Q3. So in the final transition diagram, I have four different states: Q0. Q0 is the initial state, okay, and then after Q1, Q2 and Q3. Now Q0 on a small a will go to Q1, and on a small b, it will go to Q0 itself. Take the next state Q1. Q1 on a small a will go to Q0, and on a small b, it will go to Q2. On a small b, it will go to Q2. Similarly, for Q2 state, Q2 on a small a will go to Q3, and on a small b, it will go to state Q1. On a small b, it will go to state Q1, and the final state Q2, Q3 on a small a will go to Q3 state. Sorry, here a is present, and on a small b, it will go to Q0 state. So it will go to Q0 state. So it is a small b. So you will clearly see that in the original diagram we have total 8 different states, but in the final minimal DFA we have got four different states. So 8 states is now reduced to 4 states. That's why we use minimization process in deterministic finite automata machine to get minimum number of states and minimum number of moves, so that we can save some space and save some time. Okay, so in the next video we will see a new concept in theory of automata.